for the opportunity to present today. My name is Deep Reddy Singireddy. I'm a Senior Manager SDET at Equinox. The topic I'll be walking through is governing enterprise AI systems through scenario-driven behavior evaluation. This research comes from a very real enterprise challenge. AI systems are moving from experimental pilots into production critical business functions, but many organizations are still trying to test them using methods designed for deterministic software. This creates a gap. Traditional QA assumes predictable outputs, fixed workflows, and clear pass failure outcomes. AI systems behave differently. They generate variable response, operate across open-ended scenarios, and introduce risks that are harder to detect with standard automation. Over the next few minutes, I'll cover three things: why traditional testing breaks down for AI, what a scalable evaluation architecture should look like, and how scenario-driven behavioral evaluation can turn AI testing into a continuous governance policy. The key message is simple: as enterprise scale AI adoption, trust cannot be assumed. It has to be measured, monitored, and governed. Let's start with the shift that is driving this research. For decades, enterprise software has been largely deterministic. You provide an input, the system follows predefined logic, and you expect the same output every time. The predictability is what traditional quality assurance was built around. AI changes that equation completely. AI agents are now being embedded into customer service, workflow automation, decision support, internal productivity tools, and operational systems. But unlikely traditional softwares, these systems behave probabilistically. The same prompt can produce different response across executions, and more than one answer may appear reasonably dependent on context. That variability is not necessarily a defect, it is part of how generative AI systems operate. The challenge is that our existing testing models were built for fixed outcomes, not probabilistic behavior. So the question becomes, how do we validate systems where correctiveness is not always binary, where outputs are not fixed, and where risk may appear as a pattern across many interactions rather than a single failure? This is why AI requires a new quality engineering discipline, one designed to evaluate behavior, consistency, safety, and reliability across a wide range of scenarios. Why traditional testing fails? In conventional software, testing is based on a clear assumption. Given that same input, the system should practice the same output. That allows teams to define expected outputs, automate regression test suits, and classify outcomes as pass or fail. AI systems operate differently. Large language models and generative systems rely on probabilistic reasoning. The same prompt may produce different responses, and multiple responses may be technically acceptable. That creates a different testing platform. We are no longer just asking whether one output matches an expected answer. We are asking whether the response is accurate, safe, appropriate, consistent, and aligned with the policy. Another challenge is at scale. Traditional applications usually have a finite set of workflows that can be mapped and tested. AI system has open-ended output space as prompts, user intents, context, conversions, history change. This possible behavior expands dramatically. This makes exhaustive testing impossible. So the limitation is not that traditional testing is useless. It is still valuable for integration, performance, uptime, and workflow validation, but it is not sufficient for evaluating AI behaviors. For AI, we need an evaluation model that measures patterns across many scenarios, not just like individual outputs. So, what traditional testing cannot evaluate? I would point to five major failure dimensions. The first is hallucination. A system may produce an answer that sounds confident but is factually incorrect or fabricated. Traditional tests may confirm that response is formally correct but know whether the content is true or not. The second one is bias. Bias often appears as a pattern across groups, scenarios, or users' persona. It may show up in tone, assumption, refusals, or outcomes. A small set of fixed test cases is unlikely to expose that. The third is context consistency. AI systems often operate in multi-turn conversations. They need to remember constraints, maintain coherence, and avoid contradicting themselves. A model may pass a single turn test but fails across a longer interaction. The fourth is safety compliance. Some failures only appear under adversarial prompts, requests, or edge cases. There are exactly the scenarios traditionally happy path testing tends to miss. The fifth one is the behavior variability. With AI, the same input may not always produce the same output. That makes it difficult to define a stable baseline using conventional pass-fail testing. These are not like isolated defects that can be patched one at a time. There are structured blind spots in deterministic test suites, and each one creates both a technical risk and a governance risk. If an enterprise cannot test for these behaviors, it cannot confidently govern them. That leads to the central research question again. How can AI systems be governed at enterprise scale through a rigorous, scalable testing architecture? AI agents in the enterprise. To ground this in reality, let's look at where AI agents are operating today. They are already being used in customer facing like chatbots, virtual assistants, voice agents, automated phone systems, workflow automation, and decision support engines. There are not peripheral use cases. In many organizations, they are becoming some of the first and most visible touch points between the enterprise and its customers, employees, and partners. A chatbot may answer product question or resolve service issue. A voice agent may handle real-time customer support. A workflow agent also may summarize document, extract information, trigger next steps, or update records. A recommendation may influence decisions that previously required human judgment, and all of these. There are some risk factors. A hallucination can create misinformation at scale. Bias can produce unfair or discrimination outcomes. A safety violation can create a regulatory or brand exposure. An adversarial prompt can manipulate the system. The point is that these risks become more serious when they appear in high visible, high volume enterprise environments. A hallucination is a sandbox in a real model quality case. A hallucination in a product customer service system can become an operational, reputed, and compliance issue. That is why AI quality cannot be treated as financial checklist. Before deployment, it has to become a continuous governance policy. Proposed innovation, test architecture as governance. This is where the research moves from problem to solution. The new approach I'm proposing in this is organizations needs to stop treating AI testing as one-time project activity and start building it as a persistent enterprise platform. In other words, AI testing should be an always and governance layer that evaluates AI behavior continuously and independently. There are four principles behind this approach. The first is independent evaluation. Testing should operate separately from model development. This creates separation between the teams building the system and the functions responsible for validating it. The second is organization-wide standards. Many AI systems today are evaluated using by criteria defined by individual teams. That creates inconsistency. A governance platform should apply common behavioral metrics across systems, business units, vendors, and any use cases. The third is continuous governance. AI systems do not remain static after deployment. Prompts change, retrieval source change, models are updated, and user behavior evolves. Testing must therefore continue after release through monitoring, regression testing, drift detection, and escalations. The fourth is model independent. Enterprise will use multiple vendor models, modalities, and development patterns. The evaluation layer should work across the ecosystem without needing to be redesigned every time the model change. Together, these principles change the role of testing. Testing is no longer just a checkpoint. At the end of development, it becomes a standard governance function for enterprise AI. Unified evaluation architecture. Most large enterprises do not run just one AI interface. They run many at the same time. There may be a chatbot, voice agent, there may be a telephone systems, internal assistants, workflow agents, and emerging multimodal tools. So these challenges in these systems are often owned by different teams, built on different platforms, and evaluating using different standards. One team may focus on hallucination, another can focus on compliance, another on maybe customer experience, and another on maybe bias detection. Individually, these efforts may be useful, but across the enterprise, they create fragmented quality evidence and inconsistent governance. The architecture I'm proposing addresses this through a single evaluation layer that spans every AI channel. Whether the interface is text based, or voice based, or phone based, or workflow based, or it could be a multimodal, it is evaluated again as the same behavioral metrics. This is more efficient, but efficiency is not the main point here. The main point is governance. When standards drift across channels, gaps appear. A chatbot may comply with policy while a voice agent gives a risky answer. One team may catch hallucinations while other team misses it, right? So these inconsistencies are exactly what auditors, regulatories, or customers and advisor users may eventually find. A unified evaluation architecture closes this gap by design. It gives the enterprise one consistent way to measure and govern AI behavior across every interface. Scenario driven behavioral evaluation framework. Now let's get into the methodology itself, SBEF. The key shift is moving away from validating a single output and instead of measuring patterns of behavior across many executions. Traditionally, testing asks, was this one answer correct for AI systems? That is not enough. A model may answer correctly once and fail under a slightly different prompt, a different context, or a repeated run of same scenarios. SBEF framework asks a broader question. How does the systems behave like systematically across hundreds or thousands of realistic scenarios? The framework works in three stages. The first stage, generate scenarios. This includes normal user prompts, ambiguous questions, edge cases, adversarial inputs, and high-risk situation. Second, execute repeatedly. The same scenarios are run multiple times to capture behavioral validation rather than a single response. Third, measure distributions. The results are scored across scalability, safety, stability, context consistency, bias, and maybe compliance. So these gives enterprise something traditional testing cannot provide, statically confidence in AI behavior. Instead of relying on one time result, SBEF provides evidence that is repeatable, measurable, and auditable. That is critical because enterprise AI quality is not only a technical concern, it's also a compliance risk and a governance concern. Simulation driven testing. The goal is to create broader and more realistic coverage than a handwritten test suite can provide, right? So the scenarios include ambiguous questions with multiple validation interpretations, adversarial prompts designed to trigger policy violations, multi-turn conversations that text context retention, context switching that exposes coherence failures, and synthetic user personas that reflects diverse demographics and interaction styles. Simulation matters because real users do not interact with AI systems in neat, predictable ways. They ask unclear questions, change topics in between, provide incomplete information, challenge the system, and sometimes attempt to manipulate it too. Traditional testing depends on the scenario someone thought to write in advance. Simulation expands the test coverage by generating many more interaction patterns, including edge cases and emergent behavior that may not be obvious during design. It also makes testing more realistic. Instead of evaluating artificial prompts in isolation, the system is tested against conversations that better reflect enterprise use. From a governance perspective, uh, simulation has either major advantage, reproducibility. The enterprise can generate controlled, repeated test conditions at scale. That means results can be completed across model, releases, different teams, and time periods. So simulation driven testing is not only a way to find more failures, it is a way to create defensible evidence about AI behavior under realistic conditions. Now let's see behavioral metrics framework. To operationalize SBEF framework, we need to concentrate on measurable metrics. This research defines six core metrics. The first is response reliability, which measures whether the AI systems complete tasks consistently across repeated executions. The second is hallucination rate, what measures how often the systems produce false or unsupported information. The third is safety compliance, which tracks whether responses follow policy, regulatory, and organizational requirements. The fourth is context coherence, which measures whether the systems maintain consistency across multi-turn conversations. The fifth one is bias detection, that evaluates whether outcomes differ unfair across user groups, personas, or demographic signals. The sixth is interaction efficiency, which measures whether the system resolves tasks clearly, consistently, and without unnecessary friction. These metrics matter because they connect technical evaluation to business governance. Reliability supports operational dependency. Hallucination detection protects accuracy and trust. Safety compliance reduces regulatory exposure. Context coherence improves user experience. Bias detection supports fairness and accountability. Interaction efficiency helps, controls cost and service quality. The goal is to report AI quality in language that executes risks, compliance teams, and engineering team that can all understand. Now let's see continuous quality engineering. Testing at a single point in time is not enough because AI systems can drift after deployment. Production behavior is where many risks actually occur. User behavior changes, prompts evolve, models get updated, retrieval source shift, and many failures occur or emerge. This is why this framework includes two complementary capabilities. The first is behavior observability. This is a persistent monitoring layer that captures and analyzes live AI behavior in production. It includes structured interaction logging, statistical drift detection, bias and fairness monitoring, and automated compliance reporting. The second is adaptive testing. This is a test generation capability. that evolves as the AI system evolves. When production monitoring detects failures, edge cases, or unusual behavior, these observations can feed back into scenarios generators. Together, this creates a continuous governance loop. Production behavior informs testing, testing strengthens monitoring, monitoring identifies new risks, and these risks become new test cases. This is what makes the architecture continuous rather than a one time audit. The enterprise is not simply asking, did this model pass before launch? It is continuously asking, is the system still behaving until acceptable boundaries? So that's the question. Let's summarize the three core contributions of this work. The first contribution is test architecture as AI governance. This reforms quality engineering from a project level activity into a persistent enterprise governance platform for AI systems. The second contribution is unified multimodal evaluation. The architecture is designed to span chatbot, voice agent, telephone AI, workflow agents, and future modalities under a common set of behavioral standards. The third contribution is scenario driven behavioral methodology or SBEF. This provides rigorous and repeatable methodology for evaluating probabilistic AI systems using behavioral distributions rather than a simple pass-fail outcome. Taken together, these contributions create a practical path for enterprise AI governance. They define a new way to think about testing, an architecture to scale it access the organization, and a methodology to execute it consistently. What are all the benefits for organization? So the first benefit is more reliable AI deployment. Organizations can evaluate behavioral statistically before and after release, rather than relying only on a limited test case or a pilot feedback. The second is regulatory readiness. The framework creates audit ready evidence showing how AI systems were tested, monitored, and governed. The third is customer trust. Consistent, safe, and fair AI interactions protect the customer experience and strengthen confidence in the brand. The fourth is reduced operational risk. Early detection of hallucination or bias or conflict drift or policy violations help prevent small model quality issues from becoming larger incidents. The fifth is scalable AI governance. As the enterprise adds more AI systems or models and use cases, the same evaluation architecture can expand within it. These benefits speak directly to the question leadership teams are asking now. Can we trust our AI? Can we prove it is being governed? And can this approach scale as of our AI portfolio grows? Yes. Let me bring all of this together. The shift to probabilistic AI requires a corresponding shift in the enterprise quality engineering. Traditional deterministic testing remains useful, but it is not enough to validate AI systems with open ended outputs, variable behavior, and evolving risk profiles. Behavioral evaluation provides the next steps by measuring distribution of behavioral across realistic scenarios. Organization can gain statistically meaningful evidence about reliability, safety, forgiveness, and compliance. This is also where testing becomes governance, right? When evaluation is independent, continuous, standard, and model drift, it becomes part of the enterprise context. SBF provides a practical methodology for doing this. It allows organizations to generate realistic scenarios, execute them repeatedly, measure behavioral distributions, and produce auditable evidence. The main takeaway in that enterprise AI can govern by assumption or isolated test results. It requires a scalable testing architecture that continuously measures whether AI systems behave within the acceptable boundaries. That is the foundation for trustworthy AI at enterprise scale. I'll frame two questions to guide this discussion. The first one: how can organizations establish scalable governance framework to continuously evaluate AI systems for reliability, compliance, bias mitigation, and operational risk? The starting point is treating governance as infrastructure, not as a project milestone. That means centralizing the evaluation function so every AI system is accessed through a consistent and independent layer. It also means standardizing the metrics before standardizing the tools: reliability, hallucination rate, safety compliance, and efficiency. This means two same things across chatbots, voice agents, workflows, and other AI interfaces. It also requires continuous monitoring, not just like pre-launch testing, right? AI systems can drift after deployment, so governance has to include production observability, regression testing, escalation when behaviors across acceptable thresholds. Question number two: what role do scenario-driven behavioral testing, observability, and continuous monitoring play in detecting model drift and maintain trust in enterprise AI deployment? These three capabilities work together as a closed loop. Scenario-driven behavioral testing establishes the baseline by running diverse, adversarial, and multi-turn scenario repeatedly. These organizations get a statistically picture of normal and acceptable system behavior. Observability detects deviation from the baseline in production. Structured logs, behavior analytics, and drift detection help identify challenges caused by model updates, prompt changes, data shifts, or new user behavior. And the third one, the continuous monitoring turns detection into action. When failure appears in production, those cases can be feedback into the scenario generator, expanding the test suite and improving future coverage. This is what created trust, right? Stakeholders do not trust AI simply because it passes one test before launch. They trust it because the organization can demonstrate continuously and with evidence that the system remains within approved behavior boundaries over time. Thank you for all your time and attention today. The key message I wanted to leave with you is AI governance must be engineered, not assumed. As AI enterprises adopt AI agents across customer facing, operation, and decision support workflows, trust will depend on measurable behavioral evidence. Scenario-driven behavioral evaluation provides a practical path to the trust. It allows organizations to test under realistic conditions, monitor them continuously, detect drift early, and governance risk at scale. The approach helps leaders balance innovation with accountability. I appreciate your time and welcome further discussion on how this framework can be adopted for enterprise AI quality engineering, compliance, and operational governance. Thanks again.